Okay, so another method for discussing, sorry, if for highlighting whether or not the software is working as expected, is using a dry running process or trace table. Now, what is dry running? Dry running is referred to when we run the code by not actually running the code on a program or a software or in some environment on a computer. Basically, what it means is that I'm going through the different paths or different lines of my source code and simply inputting values in what is known as a trace table, right? Like so. By doing so, I can possibly highlight whether or not my trace table is or my algorithm is working as expected. So basically, I am running through the entire code by not really executing it on any computer. It's written possibly in this pseudocode version, and I am simply plotting values in this trace table, and based on the values or the final results in the trace table, I can highlight whether or not my algorithm is working properly. Now, for a trace table to, this is also known as a walkthrough technique, in which you simply going through the entire algorithm, giving it different values and seeing how the individual variables change their states during the execution of the program. And if those changing of states are as expected, and you can say that the algorithm is working just fine, or the program is just working fine. Now, for there are certain rules for trace tables, and for understanding those rules, we'll look at this trace table that basically involves the bubble sort algorithm. And in fact, it is the efficient bubble sort algorithm in which I will be sorting this array. Okay, first thing to understand here is that my trace table is represented in the form of these columns. Uh, every time a variable changes its state, an entry has to be made in these columns. So if I don't make an entry, so for example, you can say that this variable over here, max index, is assigned with 7. So whenever an assignment takes place, as you can see here, max index is assigned with 7. Whenever an assignment takes place, I make an entry in this table over here. So if I don't make an entry, and you can see here, there's only one entry for max index here. There's no further entry. What that means is that max index, the value for 7 is being, max index 7 is being carried out all the way through the entire trace table. So there's no change. It's remaining 7 throughout the trace table. So whenever an assignment takes place and I don't write the value again, so that means the previous value is being used. So for example, n is being 6 here, and it's 6 all the way throughout here. Only here it's being changed to 5. It becomes 4 here, then 3 here, then 2 here. So if it's not being changed during this place right here, it remains 4. If it's not being changed, it remains 3, so on and so forth. Secondly, all new lines, every time you have a new line, a new row in the trace table, that really usually corresponds to a new iteration in a loop in your algorithm. So whenever you start a new iteration in your loop, that means you have to highlight a new line in my trace table. So that's exactly what's happening over here. And after that, this is basically all the variables and array index positions that are being used in your algorithm. They correspond to different columns in your trace table. So any change in these values will be represented here. Now let's see what's happening here. So just a quick go through of what a bubble sort algorithm is. The first line is basically highlighting how many elements there are in my array. I give my n element because I want my inner comparison to only stop at n to avoid accessing an index position that does not exist. I initialize my n, I assign my n once one value less than my max index. So my n will become 6 here. My outer loop, which is meant to control the passes, is a repeat until loop, and we will keep on going until no more swaps becomes true. I will assign no more swaps true at the start of this loop. And if because of this inner loop it remains true, that means at no point at this condition was true that any element was out of order, because of which at the end of this for loop my no more swaps will remain true and I will exit the loop. However, if there is any swapping take place, that will be highlighted in the inner loop. The inner loop is a for loop that simply runs from index position 1 all the way to end. So in this case, it will run from 6. So basically what I'm doing is that in my for loop, I'm comparing my first element to the second element to the third element to the fourth element, and sixth element to the seventh element. If this condition is true at any point, that means my elements are out of order and they require swapping. If swapping takes place, this is how it will be done. I will use a temporary variable as discussed very earlier on. And if swap has taken place, I will say no more swaps is false. Because of which, if I come back here at the end of my for loop, this condition will not be true, and I will come back and run another pass. Because my no more swaps is not true, it is false. I will come back and run another part. And when I run another pass, I will assign my no more swaps as true again. And this time, if my for loop runs and at no point in this condition is true, that means I will not enter here. And if I don't enter here, this no more swaps will never become false and it will remain true because of this. And when this condition is tested, it will turn out to be true and I will exit my bubble sort algorithm altogether. So this is the efficient bubble sort algorithm as discussed before. In fact, the version we discussed was including while loop. So you can do it either way. It doesn't matter. While loop and repeated the loop, they work just equally fine. They do not run any passes. In fact, you can say that repeat until loop there's even one less pass than while loop. While loop has to run one extra time just to make sure that no more passes were required, but repeat until stops instantly. If no, it doesn't even go that extra pass. You can say that in a way repeat until is more efficient, but when we talk about Python, repeat until doesn't exist in Python. We have to eventually convert back to while loop. So anyway, so now let's see how this algorithm corresponds to this trace table. So let's just say this is my array right here, and we have the elements 5, 34, 98, 7, 41, 19, 25. So max index is assigned with 7 as mentioned over here and becomes 6 as mentioned over here. This array already exists. Now, no more swaps has become true. And now what I'm doing here is okay, this column usually is not mentioned, but right now it's just simply telling you that this is actually since trying to explain to you how it is working, but usually this is not in your exam. This will not be part of your trace table. You don't necessarily have to mention it either to show what lines are being executed right now or not. This is just to give you what just to give you an idea of what's happening right now. So you can see here that line number 1 and 2 is being executed, because of which I'm assigning max index with 7 and end with 6. After that, my repeat loop starts. And in my loop, I'm going to be executing line number 3, which causes my repeat loop. Line number 4, I assign my no more swaps is true. That's happening over here. And for line number 5, in which my J is starting with 1. Now, check this out. My J is 1 because my for loop starts. My J starts at position 1. Then line number 6 initiates and I'm testing, is 1 greater, the my list first position element greater than the second position element? Is 5 greater than 34? False. Does not happen. This condition is false. In which case I will come back here, and since this condition is not true, I will not do any swapping, and I will come back to end if and line number 13 executes and my J is incremented right here. So after that, I will go back up here, start the loop all over again with J as 2. Now I'm comparing the second element with the third element. Is second element greater than third element? Again, false. I will come back to 12 and if an increment J This time I'll go for j is 3. Now is 3 is third element greater than fourth element? Yes. Now we see this. Now a condition is true. Let's see what's happening here. Because now this condition is true, my jth element, which is 98, will be assigned to temp. You see, the jth element is assigned to temp, and my j plus first element is assigned to j. So j plus first element is assigned to j, and then temp element is assigned to j plus 1. So 98 will be assigned to j plus 1. And you can see here, my these two elements become swapped here. So from this point onwards, index position 3 will have 7 and index position 4 will have 98. So this data has been changed and updated to this position right here. So now after that, after this condition, the next thing we have, we go from no more swap. Yeah, since I have done swapping, my no more swaps has been assigned to false. My j has incremented to 4. Now what I will be doing next is I'm comparing my fourth element, which is 98, with my fifth element, which is 41. As you can see here, 98 is also greater than 41, in which case jth element comes to temp right here, and my 90, if j plus 1 element comes to j, and temp element comes to j plus 1, swapping takes place, and my no more swaps is assigned with false again. J is incremented to 5, in which case now I'm comparing 98 to, sorry, j plus any fifth element with sixth element. I'm comparing 98 to 19. Are they out of order? Yes, they are. Is swapping required? Yes. 98 will come to temp, j plus 1 element will come to j, and temp element will go to j plus 1, and no more swap has become false again. J will be incremented to 6, and this time I'm comparing sixth element with the seventh element, 25. Are they out of order? Yes, they are. J will element will come to temp, j plus 1 element come to j, and temp element will go to j plus 1. Swapping takes place, so no more swaps becomes false. Now since my this first pass will run only till 6, my loop has terminated one time. My inner loop has terminated one time, in which case I will come here after I will exit the for loop, and my for loop, after exiting my for loop, this should be an end for over here. So anyway, after end for, what I do is I decrement my n by 1. So my n was 6, now n becomes 5. So that's what, if you remember, what this line does is basically causes my this element to be ignored in the next pass, because this element has reached its destined position. So my next pass will only run till 5 times. So again, when my loop runs again, I will say no more swaps is true. As you can see here, my j becomes 1. Now this time around, I'm comparing my first element, which is 5, with 34. As you can see here, 5 and 34, they are in order, so there's no swapping required. False. Then j becomes 2. I'm comparing 2 with 7. See, updated value of 3, 2 and 3 is 7. So 34 and 7 are out of order, in which case my 34 and 7 are out of order, in which case my jth element will come to temp, 7 will come to j, and 34 will be assigned to j plus 1, and swap has taken place. So I will say no more swaps is false. J is incremented to 3. Now I'm comparing my third element, which is 34, with my latest element, fourth, which is 41. Now 34 and 41 are in order. They are in order, so I don't need to do any more swapping. I will increment to 4 directly. Now fourth, I'm comparing my fourth element, which is, by the way, 41, and I'm comparing it with 19. My latest element is 19 over here. So 41 and 19, yes, they are out of order, in which case 41 will arrive at temp. I will bring jth element is j plus 1 element to j, which is 19, comes here, and temp element will come to j plus 1, and this swap has taken place. I will say no more swaps is false. J is incremented to 5. 5. Now, fifth, I'm comparing the fifth element. By the way, the latest fifth element is 41 with the sixth element, which is 25. Now, the latest element for sixth element is 25. As you can see here, 41 is not bigger, is bigger than 25 and belongs after 25. So it's out of order. My jth element will come to temp, and j plus 1 element will come to j, and temp element will go to j plus 1. And because of which now 41 has reached its destined position at index position 6, and my loop has terminated again. So now, since swap has taken place, I will say no more swaps is false. My for loop has terminated one more time. This time I will decrement n to 4, and I will reset my no more swaps to true. Now again, one more time, 1 at j is 1 now, latest elements of 1. So at first position now, the latest position of first element is that my first element has 5 in it. Yes. So is 5 greater than 7? No, it's not. So 5, I'm comparing first with second. 5 and 7, they're in order, so that's okay. I'll go to 2. I'm comparing 7 with the latest element, that is in third position. Now third position is, that's 34. So I'm comparing 7 with 34. Yes. Is it 7? 7, 7, 7, 7. This is all the way 7. 7 and 34 are also okay. They're in order. So no need to change. Then we move to index position 3. Comparing 3 with the fourth element. Now this is out of order. 34 is greater than 19 and they need to be swapped. Because of which 34 will come to temp. Jth element will have 19 in it, and j plus 1 will have temp in it. Swap takes place. False. No more swaps is assigned with false. Move on to the fourth position. Compare the fourth element with the fifth element, which is 25. Out of order, yes, they are. 34 comes to temp. Jth element has j plus 1 in it, which becomes 25, and j plus 1 will be assigned with temp. 34 comes here. My inner loop is finished. 34 becomes in its destined place, and we will stop right there. The inner loop has finished again with the no more swaps becoming false again. Then I will move towards the third, another pass in which my n will become decremented further. No more swaps is reset to true. Now I have the first element, which is 5, second element, which is 7, third element, which is 19, and fourth element, which is 25, fifth element is 34, sixth element is 41, and seventh element, which is 98. Now, apparently this looks in order, but if I do any comparison, I will compare first with second, second with third, third with fourth, and in those comparisons, I will not find anything out of order, because of which at no point this condition will be true, and at no point will I do any more swaps, and at no point my no more swaps will be assigned with false. It will remain true, because of which this does not change. And when my this time around, when my for loop terminates, my no more swaps is because it's still true. I will no longer require any more passes, and my bubble stored algorithm will come to an end over here. But at the end, before coming to an end, I will have to decrement n one more time, because the loop ran, no more swaps happened, that's okay. But the for loop ran, it terminated. But when the for loop terminated, I decremented n one last time before exiting the bubble sort algorithm completely. So this n is equal to 2 is because of this last decrement that takes place. But it's another case that I don't need any more passes, but this decrement will have to be shown here. So make sure that you enter this decrement part over here. So this is how basically your trace table will look like. It's tricky at times, but with practice, it makes it pretty obvious. But just some tips here is that always consider the last value of particular column. That will be considered. So for example, in the latest state, index position 4 has 25 in it. Index position 5 has 34 in it. And six, for index position 6, the last value is 41. For index position 7, the last value is 98. So the last value, only the last value matters for each column or each variable. So for example, n, the n for the last value of n is 32, and the last value for max index was mentioned here, and it is not changed afterwards. So only the last value has to be considered. So do not confuse this and do not be considering these values originally. The last values are mattering only.